Hey kiddos, here's the final exam review for your Algebra 2 final exam. There are a couple things I'd like to remind you of, one of which is that you can take the reference sheet that you have and write whatever you'd like on it. That's going to be really helpful. I highly recommend that you write some example problems and that you will have access to the formulas that you need, including log sines, log cosines. Okay. First up, we got to find the value of trig functions, and the big idea here is that we got to set up our triangles. So theta is looking at this angle. That means you've got the opposite, the adjacent, and the hypotenuse. Sine is opposite over hypotenuse. So here we're looking at 7 over 25. Since we're looking just for the ratio, that's it. Number 3, same thing. Here my theta has moved to there. Tangent is opposite over adjacent. So we're looking opposite, hypotenuse, adjacent, 7 over 24, and we are done. For number 5, we're looking at cosecant. We got to know that cosecant is the reciprocal of sine. So if sine is opposite over hypotenuse, cosecant is hypotenuse over opposite. Here's our angle. There's my opposite. Here's my hypotenuse. Here's my adjacent. Hypotenuse over opposite would be 17 over 15. For number 7, we got to find the measure of the indicated angle. And again, here we're looking at the opposite, the adjacent. Those are the pieces that we know here. That's going to be a tangent function. So tangent of question mark is equal to 6 over 8. That means we're looking at tangent inverse of 6 over 8, which, to be honest, is good enough for your final answer, although it's really nice if I can see that a little bit more clearly. So we got arctangent of 6 divided by 8, and that's going to be 36.86 or 869, so 36.7-ish in terms of that. For number 9, we're going to find the measure of the indicated side. Here we've got our angle that we know, although you could certainly find the top angle and do it that way as well. And here we're looking for the hypotenuse, and we know the adjacent. That's going to be a cosine function. So cosine of 50 is equal to adjacent 12 over hypotenuse x. Going to multiply both sides by x. We get x times cosine of 50 is equal to 12, and we're going to do x is equal to 12 divided by cosine of 50. If you would rather have that as a decimal, that's fine. Cosine of 50 is going to be 0.64. 12 divided by cosine of 50 is going to end up, sorry, I'm having some typing issues. 12 divided by cosine of 50 is 18.66. So x is looking at 18.66 or 18.67, depending if you're rounding or truncating. Next up, we've got a word problem. Here we've got Bobbert flying a kite, and Bobbert is letting out 47 feet of string. So string goes to the kite up here. We've got a 35-degree angle with the ground. And how high off the ground was the kite? That's what we're looking for. We know this is going to be a right angle because we're talking about height. So we've got opposite and hypotenuse. This is a sine function. Sine of 35 is going to be x over 47. 47 multiplied by sine of 35 is going to be our x value. You can leave it like this, or you can type on your calculator 47 times sine of 35, which is 26.95. 26.95. And this is going to be in feet. For 13, we're using the law of sines, and here we're being asked to find AB. That's this value up here, so I'm going to label that C. And here we've got enough information with B and C together. Just as a reminder, if you need to, you can always find that third angle by using a triangle as 180 degrees. But here we've got sine of 113 divided by C, is equal to sine of 31 divided by b. And I just used b instead of 14 because that's what I said instead of doing what I was looking at. Okay, sine of 113 is going to be 0.9205 over c, and sine of 31 divided by 14 is going to end up being 0.0368. Multiply both sides by c to get that out of the bottom, and we're going to end up with c times 0.0368, and if I divide by that, 0.9205, we end up getting c is equal to 0.0368, 25.01. And looking at my other sides, 14 is opposite 31. This is a much bigger angle, so a much bigger side makes sense. All right, find each measurement indicated. Here we're looking for an angle. And we have to use law of cosines, although I don't know that it actually says that here. Ooh, I forgot to indicate that. These two are meant to be law of cosines, so I apologize for that. Although you could figure that out pretty quickly if you try to use law of sines, you don't have enough information. So if we're looking for b, I'm going to set up my law of cosines as the b version. So b is by itself, then we've got a squared plus c squared, and then minus, I'm going to use the same letters as here, 2 times a times c, and then I'm going to use the cosine of the angle that goes with one on the opposite side, times cosine of b. So plugging stuff in, we've got b, a, and c, 100 for 10 squared, a, 18, so 18 squared is going to be 324, 25 squared is going to be 625, these are really big numbers, minus, I don't know why I'm doing these all out instead of writing these, but that's okay. So 2 times 18 times 25 is going to be 900 cosine of b. Just as a reminder, we've got to keep this stuff together and move the other things to the other side. So when I do that, so that's going to be 100 minus 324 minus 625. We get negative 849 is equal to negative 900b. Dividing by negative 900. So negative 849 divided by negative 900. We end up getting 0.9433 is equal to, I lost my cosine there. Wow, that's fun. Cosine of b. We know we have to do inverse cosine, so cosine inverse of 0.9433 is going to be 19.38 degrees. All right, next up we got to convert things into degrees and radians. You should have a formula written down for this. So degrees is equal to 360 divided by 2 pi, that's our ratio here, and that's times radians. To get radians, it's going to be 2 pi over 360, again that's our ratio, that's a whole circle, times degrees. So that's what we're looking at here. We've got radians is equal to 2 pi over 360 multiplied by 120. We know that's 120 over 1, so this would end up being 240 pi over 360. That actually reduces kind of nicely because the zeros cross out. 24 over 36 is going to be 2/3, and then we got pi. As soon as you get there, you are good, though. Converting into degrees, we said that's going to be times 360 over 2 pi. First thing I'd like you to notice is that the pi's cancel out. And then we've got 4 times 360, which is going to be 1440. And that's going to be over 3 times 2, which is 6. And pretty sure that divides evenly. If I do 1440 divided by 6, we get 240 degrees. If I take a look at the next thing, now we're on to logs. If we're evaluating, that's when we write this as equal to an exponent. We've got 7 to some exponent is equal to 49. That exponent is going to be 2. Since 7 squared is 49, e is going to be 2. That's our evaluate step. Looking at 23, same thing. That's going to equal some exponent. 2 to the e is 32. That means that 2 to the 5th is 32. Our exponent is 5. For number 25, we're converting from exponential to logarithmic form. So we've got b to the e is equal to a, and our friend the log of some base of an argument is equal to an exponent. So here our base would be y, our exponent would be x, and our argument would be 103. So you've got log base y of 103 is equal to x. For number 27, we're doing some condensing. First thing, I'm going to take my numbers out front and write them as powers. I only got one here, I guess. So that's log base 4 of a squared minus log base 4 of b. Since we're subtracting, that really means dividing. I'm going to write this as log base 4 of, we got a fraction. Here we've got a squared and b on the bottom. Doing the opposite, we're going to expand. And I'll do 30 since 29 is the opposite of what we just did. So here we're going to expand based on multiplying. That means I'm going to add. So that's log base 8 of x plus log base 8 of y to the third. We can bring the power down front. We get log base 8 of x plus 3 log base 8 of y. All right. Next up, we've got to solve each equation using the relationship between exponentials and logarithms. The log's already by itself, so I'm just going to start this off by converting. And when I do that, we get 5 squared is equal to p minus 3. If I add p to both sides, we get 25 plus 3, which is 28. That's equal to p. Next up, we got to solve using common bases. I've got 216, I've got 36. Well, I know 36 is going to be 6 squared. I don't think 36 squared is going to work for that. It's going to be a really big number. So I might look at this and then 6 to the third, 6 times 6 times 6 is 216. So that gets us in really good shape really quickly. Okay, so we've got 6 to the third to the negative m minus 3. That's equal to 6 squared, m plus 3. That'll give us, when we use exponent rules, we got to distribute, so minus 3m minus 9 is equal to 2m plus 6. Bringing the 3m to this side, we got 5m, and the 6 to this side, we get minus 15. That tells us that m is going to be negative 3. Okay, here you're given a mother function, and the mother function looks something like this. And you're also given the asymptote at 0. You're asked to then graph this plus 2. That's adding at the end. That means this whole thing is going to be going up 2. So my asymptote is going to be at height of 2. The point that would be at 0, 1 would now be at 0, 3, and the point that would be at 1, 3 would now be at 1, 5. You need 2 points, you need the asymptote, and you need the shape. and actually hit your points, hopefully. Next up, we've got some exponent rule stuff. You got to distribute this to both pieces. The hard part is remembering to do this to the 8. So 8 to the 1/3 times m to the 9x times 1/3. The tricky thing here is that 8 to the 1/3 is reducible because 1/3 is the same thing as the cube root of 8, which happens to be 2. The other part's a little bit easier. 9 times 1/3 is going to be 9 over 1 times 1 over 3, which ends up being 9 over 3, which ends up being just 3, and I keep the x. Definitely want an example like this, because there's a problem really similar to this on your final that I think is likely to cause some issues, especially around that part. So please have that as an example. Next up, we got to solve a rational exponent equation. And here we've got 486 is equal to 2m to the 5/3. We're going to do the same thing we always do for any equation ever, and that's going to be get this weird thing by itself by dividing by 2. If I divide 486 by 2, I get 243 is equal to m to the 5/3. And here we got two different options. A good chunk of you likes to just do this in one step on your calculator. That's totally okay. And to do that, we're going to then raise both sides of this to the 3/5 power. Just be really careful. This is a power. This is not multiplying. So we are not going to get 243 times 3/5. This is 243 to the 3/5 power. And when I do that, so on my calculator, I get 27 is my answer. At that point, you're done. A good number of you also prefer to do this instead of this way, but by rewriting this as a radical expression instead. So 243 stays the same, and m to the 5/3, we know that the third on the bottom becomes a cube root, and then we've got m to the 5th on the inside. Based on the way that I wrote this, we're going to end up with a really big number first, and that's okay. I tend to prefer doing this the other way, but I wrote this backwards, but that's fine. We're going to raise both sides to the 3rd power. 243 to the 3rd power is going to be 143,48907, and that's going to be m to the 5th. And then the 5th root of this is going to end up being 27. If you are not sure how to do a 5th root on your calculator, you can talk to me and I'm happy to work you through that. If you had written this backwards, or the other way around, which we can do this a third way, I guess, because why not? We get 243 is equal to the 3rd root of m, and then that's all to the 5th. And now, if I were to do the 5th root to both sides, we get a double stacked radical, which is kind of weird. But the 5th root of 243, 3 times 3 times 3 times 3 times 3 is 243. So that would give us just 3. And here the root and the power cancel out, leaving you with just the cube root of m. To get rid of the cube root, we're going to raise both sides to the 3rd power. And when we do that, we end up getting 27 is equal to m. 3 different roots to get to the same answer. It doesn't matter which way you do that. I tend to prefer the one all the way to the right because you don't end up with an enormous number along the way. Or if I have a calculator with me, I'll do the one on the left because that takes a lot less time. For number 41, we're looking at the number of mice in a colony, and we're given an equation. I'd like us to recall that these general equations are all about the final amount is equal to that starting amount multiplied by some rate raised to some kind of time over the cycle length. So when we're looking at this, the initial starting amount is 250, so that's going to be 250 based on that, and we have our cycle length of 4. So here we're looking at weeks, And if a cycle is 4, that means every 4 weeks the number of mice increases by 1.5 is going to be 1 plus 50%. Our rates in terms of percents will always start with 1 plus that percent. So we're looking at every 4 weeks the number of mice increases by 50%. How many mice were in the colony after 15 weeks? Well, let's plug that into that equation. So if we're looking for m of 15, that's going to end up being 250 times 1.5 to the 15 over 4. I'm going to literally type this into my calculator. 250 times 1.5 to the 15 over 4. If you have a scientific that doesn't do math type, you got to be really careful with your parentheses. And when I do this, I get 1143.6. So it's going to be somewhere around 1143 mice. For number 43, we're looking at kind of doing the opposite version of this, where we're building our own equation. And we're talking about students that are sick with examitis. And on the first day of June, there are 6 students sick. Okay, that's going to be that first value. And the population of 6 students doubles, so my rate is going to be 2. And that's just the number 2. We're not doing 1 plus 2. Doubles means 100% growth, so really it would be 1 plus 1, which is 2. And every 3 days, that's my cycle. So that's my k value. So my equation is going to be a is equal to 6 times 2 to the, let's call this t over, and we said the cycle was 3. All right, and this is going to be days, and we're looking for something in days. So this is June 1st, and to get to June 11th, I guess we can think of this as either 10 days or 11 days, depending on whether we include this. I'm just going to say this is going to be 11 days. Either way, you'd get credit for this as an answer. And we're going to plug 11 into our formula there. So we've got a is equal to 6 times 2 to the 11 over 3. And when we do that, 6 times 2 to the 11 over 3, we end up getting 76-ish students. And that's it for this page. Next up, we've got to do some graphing. You will be given the mother function for these, so let me just add that in. The mother function here would be, and I'm going to zoom way in so I can actually graph this reasonably well, would be at 0, 0, and then at 1, 1, and then at 4, 2, and look something like this. It's going to go all the way, oh, wow, I actually ended that really nicely up there. So, if we're trying to graph this thing, 2 times the quantity x plus 2, this is going to be each point multiplied by 2, so that's y stretch, I can't spell, there we go, times 2, and then x plus 2 is going to be left 2. I'm only going to give you one transformation horizontally and one vertically on your exam, just because that if you have more than one each way, it kind of messes things up. So what we're going to do is to take each x value and move it 2 places to the left, and we're going to multiply any y coordinates by 2. So the first one, the y would be 0. 0 times 2 is 2. For the second one, we're going to move that to -1, but I really want to double that y coordinate, so it's not going to be at 1, it's going to be at 2. And for the third one, I'm going to move it 2 to the left, which would be at 2, then double the height to give us 4 as a value. Our new graph is going to look like this. As an alternative, one of the ways that we can do these really, really easily for us is by making an xy table, choosing the number that makes the inside 0. So if we've got x plus 2 equals 0, that tells us that -2 is going to be our first x value. Because this is a square root, I'm only asking you for 2 points. You can use the next value up very easily and get a whole number. If you're asking for a third point, you want to try to make the inside another square root. The next square root is going to be 4. So 2 plus 2 would be 4. You'd want 2 to be your third point. And when I plug this in, we get 0 as our first y value. And if I plug negative 1 in, that's going to be 2 times the square root of negative 1 plus 2. 2 times the square root of 1 is going to be 2. We get the same 2 points that we got using transformations. So if you want to check your work, or if you want to just use plugging in points, as long as you get that vertex, I'm okay with that. You're not asked for domain or range or anything, so we can move on. For number 47, we got to solve this equation. We already have the weird thing, the square root by itself. So the big question is, how do we undo a square root? And the answer is we have to square both sides. When we do that, the square root and the square just cancel out, leaving us with 2r plus 18. 4 squared is going to be 16. We've got a minus 18 to both sides, which is going to be negative 2 is equal to 2r, which means that r is equal to negative 1. You do have to check for extraneous solutions for these problems. We talked about why you might not have to, but in this case we're really talking about just check for the sake of understanding what's going on there. So we've got 2 times negative 1 plus 18 is equal to 4. 2 times negative 1 is negative 2, plus 18 is 16. The square root of 16 is indeed 4, so we are okay. For 49, we're looking at a cube root. Same thing, we're already set up as by itself. We just have to undo both sides. We're going to cube. And when we do that, we get v plus 19 is equal to 64. Getting v by itself, we're going to minus 19 to both sides, which is going to end up being 45. And we are done. For cube roots, you do not have to check for extraneous solutions because you're not doing anything to the problem that would add any of them in. On to page 7. For number 51, I guess the instructions got deleted, but that's okay. We're trying to use the notation to figure out what's going on here. For 51, we're looking at as x, this is as x approaches 3 from the right. That's what that plus means. So we're looking as x goes to the right, what's happening? Since y is going up, y goes to infinity. The second one is from the left. Oh, let me actually do that in green. And as we approach 3 from the left, we're going to end up with negative infinity because we're going down. One really good rule of thumb is that the ones that have some kind of approaching a specific value, for a graph that looks like this, if this is that asymptote, those are going to be some kind of infinity. And if you want to think about this as on the left side, it's negative, on the right side, it's positive, go for it. For the second part of this, we're really talking about the horizontal asymptote. As x approaches infinity, that means goes to the right. So as x goes really far to the right, it looks like this graph is coming down to this horizontal asymptote, which is at y is equal to 4. That means that we're approaching a height of 4. Same thing on the negative side. As x goes to the left, well, this graph is getting closer and closer to 4, so we've got 4 as an answer there. For number 53, we're identifying different parts of this graph. You don't actually have to graph it. It's just asking for your vertical asymptote, and that's going to be where the denominator is equal to 0. So the way we do that is we set that equal to 0, so minus 4x minus 12 is equal to 0. I'm going to add 12 to both sides. Minus 4x is equal to 12 divided by negative 4, and we get x is equal to negative 3. That's my vertical asymptote. Then we'll talk about the x-intercept, because that's next in order. The x-intercept is where y is 0, and we had a shortcut for where the numerator is equal to 0. So we can say that x plus 2 is equal to 0, which means that x equals negative 2 is the x-intercept. For the y-intercept, I'm going to do this here. That's where x is equal to 0. So I'm going to plug in that, and we get 0 plus 2 over negative 4 times 0 minus 12. On top, that gives us 2, and on the bottom, that gives us negative 12. And that's my y-intercept. And then finally, we've got the horizontal asymptote. That's where we plugged in really, really big numbers. So like 1,000,000 for x in both of these. And we had a shortcut for the horizontal asymptote where we looked at just that 1x on top divided by minus 4x on the bottom. And that's negative 1/4 is our horizontal asymptote. For number 55, you've got to simplify the expression. I should ask you for excluded values as well on the actual final. I don't. But here we got to do a whole bunch of factoring. I'll do the factoring out slowly just so we know what's going on. So n squared plus 3n plus 2. Just to remind us, we've got to do a times c, and that would get us 2n squared. And I'm looking for factors of 2n squared that will then add up to 3n. So we're going to multiply and add. Things that multiply to 2, pretty quickly we get 1 and 2. And since 1 times 2 is equal to 2, and 1 plus 2 is equal to 3, we're golden. That gives us a shortcut where we can just build the parentheses as is based on those numbers, n plus 1 and n plus 2. The only reason we can do that is because we have a 1 in front of that. You don't need to worry about ones that don't have that for this exam, but we'd have to use grouping as an alternative. Okay, let's now do the bottom. So we've got n squared plus 5n plus 6, same thing. A times c is going to be 6, b is going to be 5. Things that multiply to 6 and add up to 5 are going to be 3 and 2. That gives me n plus 3 and n plus 2. Okay, factored form for our fraction. Let's do that right down here so we're out of the way. We've got n plus 2 and n plus 1. I don't know why I switched the order on top. And on the bottom, n plus 3 and n plus 2. We talked a lot about excluded values. I'm going to put those here, but again, you do not need these necessarily on the exam. These are the things that would make the bottom 0, so n equals negative 3 and n equals negative 2 cannot be values. And then finally, we're talking about just getting rid of things they have in common. That's n plus 2 and n plus 2. Leave me with a final answer of just n plus 1 over n plus 3. And that's it for this page. Last page. We are looking at rational equations. I gave you a couple of examples extra for this because this is probably the hardest thing that we did this year in terms of the actual math. So we had a strategy for this. Part 1 was to always factor everything that we can, preferably in the denominator. That's the really important part. And when we do that, nothing to factor in the first one. In the second one, I can take an x out of both of these, and that's going to give me x times x plus 5. And I noticed that the third denominator is the same as the one I just had. So we're going to have x times x plus 5. And again, just for the sake of being precise here, I'm going to identify my x vals, my excluded values. And that's going to be x cannot equal 0 and x cannot equal negative 5, which will handle both of those. Okay. The most important part of this is I've got to find a common denominator. I'm going to look at each part of this fraction setup, and I see that the first one has an x plus 5, the second one has an x plus 5, the third one has an x plus 5. Because all three of them have an x plus 5, I don't need to do anything with that. I do notice that the second fraction has an x, the third fraction also has an x, but the first one does not. So to handle that, I'm going to multiply the top and the bottom by that x. I'm not going to multiply anything on the bottom actually out, because at this point I have all three in terms of the same denominator. And what we're really doing is we're multiplying by that denominator, but I'm just going to cross all three of these out, and that leaves me with just the numerators. 5x minus 1 is equal to 2. I'm going to add 1 to both sides. We get 5x is equal to 3, which means that x is equal to 3/5. Since that is neither one of those numbers, again, we don't really see problems that comes into being, but because x is neither one of those numbers, we are good. Finally, number 59, we're looking at the same type of thing, a little bit different factoring here. Here I've got a squared minus 16. We talked about this being the difference of two squares. If you're more comfortable writing this as a squared plus 0x minus, 0a minus 16. A times c is minus 16, b is 0. That gives you 4 and negative 4. That's fine. If you see this and you immediately say a plus 4, a minus 4, that's also fine. You might also notice that the other pieces give you some information that will help you with that. Okay, so now that we've done that, this is the factored form of this. Let us identify the pieces in the denominator. So a plus 4, a plus 4. This one does not have an a plus 4. And if I do that to the bottom, I got to do that to the top as well. Okay, a minus 4, a minus 4. This one does not have an a minus 4. And if I do that to the top, I've got to do it to the bottom. I've got to do it to the top as well. All denominators are the same. Let's cross them out. And that leaves us with a minus 4 times 1, which is just a minus 4, plus 4a plus 4 is equal to 1 times a plus 4 is a plus 4. Okay, let's combine some like terms. 4 and minus 4 go to 0. A plus 4a is 5a, which is equal to a plus 4. You also might notice that I skipped doing excluded values at the beginning. Just as a side note, a cannot be 4 and a cannot be negative 4. I'm going to bring a to this side, so we get 4a is equal to 4. Dividing by 4, I get a is equal to 1, which is not an excluded value. And that's it.